Okay, so you can all hear me loud and clear, right?
Yep.
Okay, thanks. And here we go. Okay, so today is March 1st, 2023, and report for lab 1 is due now. Please upload your, please upload your spreadsheet and Word/PDF document. Okay. First exam is 1 week from now. Okay, and I decided to cover just those 2 chapters in the exam, so you're not overwhelmed for the exam. Those are the sections of the exam from the book, taken from the book. And I want to, let's go quickly through that, okay, before we start the lab activity. Okay. 18.1 is just the origin of electricity, okay? And we covered that in the lecture. The important thing here is this value of the electric charge. This is the fundamental value of the electric charge. For the sake of this course, it's okay to believe that's the lowest electric charge that I'm going to find out there in nature. And that's the electric charge of the proton and the electron. Okay. That is something called the electric force. That's something, a phenomenon that has been observed since antiquity. Okay, and the ironic thing about that is that back in ancient Greece, they saw the electric force was actually a magnetic in nature. So they were mixing up the forces. They had observed magnetic forces with some stones that naturally occurs on Earth, okay? And then they start observing this funny force that whenever you rub it, 2 materials together, right? You could attract, you could exert a force. At that time, they thought that this type of force that we today call electric force was a magnetic force. So here is the electric force, attractive and repulsive. Okay, and there are all sorts of technological applications, practical applications for the electric force. That's one of them, the case of electronic ink. Conductors and insulators, there are 2 types of materials that you have to be aware of. In reality, there are 4 types of materials, but in this course, we'll be covering only 2 of them, that is conductors and insulators. Conductors allow electric charge to move easily. Insulators restrain the motion of electric charge. That's what you have to know. Metals are conductors, plastic, glass, and several other types of materials that are electrical insulators. Electrical insulators don't let electric charge to move. You can have an insulator electrically charged, like in the case of this rod here, ebonite rod. It is electrically charged, but the charges don't move easily inside the bulk of the material. Whereas in metals, in conductors in general, they do move easily. I'm skipping this one, but here they're just, let's see. Yeah, we gotta skip this one because I didn't cover that. Skip, but this is just a way for you to find out how we can charge objects. Okay. That's one possible way of charging object. Another way is just by connecting the object to a battery, for instance. and Coulomb's law that you have to know. Here's the equation for Coulomb's law, can be attractive and repulsive force. Unlike the force of gravity, they're just attractive. And this force, reigns supreme in the microscopic world. It is in the microscopic world that this force in the microscopic world, this force is larger than any other force. You can even ignore the force of gravity whenever you're dealing with atoms and molecules. So the electric field, okay. We have a question of the electric field in the quiz. So the electric field is just something that's something that's derived from the force. Whenever you put an electric charge close to another one, this electric charge is going to feel a force. But if you remove this electric charge, just like I mentioned in the course, right? Something else is left behind. You don't have a force, but something else is left behind. And this something else is called an electric field. And it is the ability of a charged object to exert a force in another charge. And for a point charge, Q, the electric field is KQ over R squared. If you have another charge, Q1 next to this charge, the force is going to be Q1 times E. So the force is just the electric field divided by the test charge. Both the electric field and the force are vectorial in nature. Okay, here we go. We have here the net electric field at this point C. Okay. Here is the force, the net force between 2 and the net field between 2 and 4. This one is the net field between 2 and 4. Here is the electric field due to point charge 1 and 3. That's charge 1 and that's charge 3. And here we have the net field. Net field of the four charges. We cover capacitors, okay? Even the parallel plate capacitor. And we even did an experiment with that. Last week was a model of the parallel plate capacitor in which you had 2 electrodes that behave just like a plate, 2-dimensional plate, which was electrically charged, electric field. So why the parallel plate capacitor is important? Because the parallel plate capacitor produces a uniform electric field. That's why it's important. In the same way that the gravitational field nearby the Earth's surface is uniform, nearby the Earth's surface, okay? And that's to that first order approximation. The electric field is also uniform between the plates of this capacitor. You can also remove the other one, right? And you're still going to have a uniform field to the right and to the left of this guy. But if you insert another negative plate here, the electric field is going to be uniform between the plates and it's going to be 0 outside the plates, outside the volume of those 2 plates. Electric field lines. Okay, electric field lines is something much more convenient to use than the electric field vectors, okay? That's why we invented the electric field lines. That's why we cover electric field lines. Instead of keep on drawing a bunch of arrows that represent vectors at different points in space, people came up with this representation of the electric field lines that's far more convenient and quicker to draw around the electric charge. The higher the concentration of the electric field lines, the stronger the electric field. That's how this thing is interpreted. And towards the charges, positive charges are sources of electric field, negative charges are sinks of electric field, right? And because yeah, in real life, that's what it happened between the plates of a capacitor, of a parallel plate capacitor, but in the middle here of the capacitor, the field is pretty uniform, very uniform. And then things can become complicated, you know? Again, this is the simplest electric field configuration you're going to see out there. For a point charge, that's the next simplest configuration that I'm going to see out there. This is simpler because the field is uniform. The magnitude of the field here is the same as the magnitude here, the same as here, and so on. Here is still simpler, but the magnitude is going to vary with the square of the distance. The magnitude of the electric field is going to vary with the square of the distance. The magnitude is stronger here, weaker, weaker, and weaker as you move further and further away from the charge. Okay. Now, things become complicated when you start to use different geometries. When you add more charges, for instance. Now you no longer have that symmetric configuration that you saw before for a point charge, right? For a 2-point charge, you have something like that. Okay, and 2-point charges, one positive, another positive, you're going to have something like that as well. Okay, and then you have these other types of configuration that involve many more charges. Okay, where there are applications for the electric field in the life sciences. One of them is the electrophoresis of DNA. Even today, I remember a professor of mine wanted me to do an experiment, electrophoresis with him in his lab. He had one of those machines there. We skipped electric field inside a conductor. Yeah, I skipped 18.8. I didn't cover that. Okay, even though it's important, but that's okay. Gauss's law. We cover some problems of Gauss's law. You have to know how to calculate the electric flux. Okay. And using Gauss's law, here you go, the electric flux is equal to the charge enclosed by a Gaussian surface divided by epsilon naught. With this technique, you can calculate the electric field. But this technique applies only to a geometry that has symmetry. You cannot solve every problem with this technique. To solve for the electric field, okay? To solve the electric flux is easy. To solve for the electric flux is easy. If you have a whatever charge distributions you have, and you create arbitrary Gaussian surface around the charge distribution, you are going to know that the electric flux is going to be the charge enclosed divided by epsilon naught. The electric flux, in a way, is easy to calculate. What is difficult to calculate is to calculate the electric field using Gauss's law. And there are a few problems out there that can be solved using the Gauss's law. And don't forget, Gauss's law is a more generic formulation of the Coulomb's law. Okay. Here are some examples that I did in the classroom. And we are going to go, let me quickly review potential energy. Potential energy, we have electrical potential energy and electrical potential. Electric potential energy is just like, is similar to the potential energy that we saw in physics 6. Okay. We have electrical potential energy of a uniform electric field. Okay, which is easier to calculate. Electrical potential of a uniform electric field is similar to the gravitational potential nearby the surface. Okay, it goes linearly the energy goes, potential energy goes linearly with the height in the gravitational field. Electrical potential energy goes linearly with the distance from one of the plates of your capacitor. Okay. So, and then you have electrical potential difference. Electrical potential difference is what we measure with the multimeter. It is a quantity that's fairly easy to measure. It was the electrical potential difference. Electrical potential difference is the electrical potential energy divided by a test charge. And that was easy to measure. The unit for the electrical potential is the volts. 9-volt battery, you have 10-volt battery, 9-volt battery, 1.5-volt battery, we have 3 volts battery, and so on, all sorts of battery. They're just telling you what the electric potential that the cell has can provide to you. And if you look at the cell, they're going to tell you also how much energy that cell has. Okay, the manufacturer usually prints that that information there in the cell itself. You got 12-volt battery of your car. Okay, 12 volts is the electric potential, and this battery has a given electric potential energy. That's usually printed in the device. Conservation of energy, because the electric force is a conservative force, we can apply principles of conservation of energy when you have an electric field in space. Okay, so we have an electrical potential associated with the electric field, so that electric potential can be used in problems using conservation of energy. Kinetic energy plus potential is equal, right, to the mechanical energy. And that's what this example is all about. We did a problem, an example like that as well. Remember, we have all those energies that you learn, right? Kinetic energy, rotational kinetic energy, translational kinetic energy, gravitational potential energy, elastic potential energy, and electric potential energy. Okay, but like I mentioned before, in the microscopic world, this potential energy here is negligible. Okay, problems that we usually do, the problem that we do usually have only those two terms, this one here and this one here. Everything else, not only this one is negligible, the other two might not be negligible. Okay, may not be negligible, but for most problems that we do, they can be neglected. Electric potential different by point charges. Okay, so you have to know the equation for two electric potentials, right? The electric potential of a uniform electric field, electric potential of a point charge. KQ over R. Here you go, electric potential of a point charge. Total electric potential, the electric potential, in order to find out the electric potential at a given point when you have several electric charges around those points, how do we calculate the electric potential due to, of those two charges at A and B, All you have to do is to find out the electric potential due to this charge at A and the electric potential due to this charge at A as well, and sum both of them. You get the same for B, for the point B. You sum. Okay, potential energy of a group of charges. I did something like that as well. Okay, if you have a single charge away from everything else, okay, nothing around it, the potential energy of this charge is going to be 0. Okay, now if you go ahead and bring another electric charge close by another one, now you have an electric potential energy. This system has an electric potential energy. We see that the system has an electric potential energy. However, if the charge is isolated from everything else, this charge alone has no electric potential energy whatsoever. Remember, I'm talking about electric potential energy. it may have kinetic energy, but when it is isolated in the universe, alone in the universe, it has no electric potential energy. It needs to have another electric charge nearby it to say that the system, right, not just the charge, but the two charges have an electrical potential energy. And if we bring a third charge, the electrical potential energy of my system of three charges, is going to be the electric potential energy between those two charges, plus the electrical potential energy between those two charges, plus the electric potential energy between those two charges. That's how you calculate the net potential energy of the system. If you have four charges, you repeat the same procedure. Okay, electric potentials, equipotential surfaces in the relation to the electric field. We discussed that in the first lab, and we're going to do something similar today. Okay, so if you have a point charge, you're going to have those equipotential surfaces around the charge, and the electric field is going to be normal to these surfaces. Normal to the surface. And normal means what? Normal means perpendicular to a surface that's tangential to this equipotential surface. Okay. Here you go, the electric potential surfaces of a dipole, as well as the electric field lines of a dipole. You can see that looks fairly complicated. Nearby this one of the charges, those surfaces are very close to that sphere, okay? But as you move away from the charge and the distance of to this charge is no longer becomes negligible, then this charge start to affect the potential in those regions as well, and the surfaces start to deviate from a sphere. Okay, notice that this inner surface here is very close to that of a sphere, right? But that's because the distance between this point and this charge is much less than the distance between this point and this charge. Okay, that's why you see behavior that almost symmetrical. But as we move away from this charge, this surfaces start to distort. Okay, start to distort because now you start to get more and more a greater influence from the other charge. Okay. Here, the equipotential surfaces for our parallel plate capacitor. You saw that. You didn't see a surface, you draw lines, right? Curves, equipotential curves. Which is, by the way, is a good model. Here you go, capacitors and dielectrics. For whoever arrived, now we are just quickly reviewing what's going to show up in the exam. It's going to be just chapters 18 and 19, okay? The definition of capacitance is charge divided by the voltage. Why capacitors are important? Capacitors are important because they're like batteries. Batteries carry energy within them. Capacitors also, they carry energy within them. And if you're smart enough, you can use that device to do some useful work. Consider the capacitor as a very simple type of battery. Batteries is something that can hold the charge for a very long periods of time. Capacitor, no, they cannot. Once you connect them to a system, to an electrical circuit, they tend to lose the charge rather quickly, unless you do something else to the capacitor. Unless you have special types of capacitors, and there are applications for capacitors. Okay, one of them is to power flashlight bulbs. Another one is in the keyboard of your computer. We have capacitors there in each of those keys of the keyboard. We have energy storage inside a capacitor. And I gave you a quick idea how to get that the equation for the energy of the capacitor. Okay, another application of capacitors in defibrillators. Capacitors are very good devices to discharge a large amount of energy in a very small amount of time. That's what their applications are for. And a battery may have more energy than a capacitor, but the battery, you cannot discharge the energy of the battery very quickly. A capacitor allows, a capacitor allows you to do that. And then we have those biomedical applications that are not going to show up in the exam, but might be of your interest. Okay. One interesting thing about the capacitors is that many cells in the body behave like capacitors. A cell membrane, for instance, behaves like a dielectric device that separates the positive charges from the negative charges, positive ions, okay, from negative ions. Here's extracellular fluid outside the cell, intracellular fluid inside. So the cell is something, as a three-dimensional device, right? It's a three-dimensional organism. And it does behave like a capacitor. Here is the example of sodium channel. And here's another application of physics, electrocardiography, in which you measure the electric potential or the potential difference in the human body. We also have electroencephalography. There's a similar device, right, that also measures the electric potential difference, but it does that in the brain. You see what electrical potential can do, the measurements of electrical potential. In principle, you can use a multimeter to make those measurements, in principle, right? And we also have this other device called electroretinography that measure also the potential difference of the retina. Okay, electrical characteristics of the retina of the eye lead to potential difference measured in electroretinography. So all those ideas, they exist because they're useful. Okay, we can apply those ideas to devices that can make all sorts of measurements. Electrocardiogram, electroencephalogram, electroretinogram. And then the last one, we didn't cover it either, so I'm not going to ask that. But it's just like a very important experiment, which is the Millikan oil drop experiment. It's a historical experiment. Okay, this guy discovered that the electrons, the electric charge of any object is quantized. That very first principle we saw before. Quantized means charges occur in the nature in terms of integer numbers. Integer numbers in terms of the fundamental charge. Okay, so that's the last one in the chapter. The list of the sections are here. Okay. And now we're going to have our electric field lab number 2. Okay. So I want you to download, let me see what I did there. Yeah, P07, okay. P07 lab 02 GXX in your group folder, XLSX. Okay. 18 students here. Let me get my roster.
Professor?
Yeah.
Should that already be in our Google Drive?
What? Yes. You're talking about the spreadsheet, right?
Yes.
Yes, it is in there. Can't you find it?
No, I just see our two that are due.
Okay, here you go. L02, group 3, right? You saw that, right?
Let me refresh the page.
Group 1, here you go. Group 1, P07, L02, G01, okay? Group 2, P07L02G02. Group 3 already saw that.
Yeah,
Okay.
on my end, I don't see it.
You still don't see it?
No, sir.
Well, I can't see it here. Check with your other group members, see if they can see it.
Okay.
Maybe there might be a problem there with your computer. Okay, group 5 is here. Group today is, yeah. See, physics 07, yeah, no problem. Group 7, yeah, it's all here. Let me go one by one. 07.
Okay. I'm getting from other members of my group that they don't see it either.
Really? Get there. Let's figure out what's going on. Let's sort out what.
Thank you.
Okay, force meeting. Randy, are you there, Randy?
Yeah, I'm here.
Okay, good. So do you see the spreadsheet there in your group folder?
No, I don't see it.
What's going on here? Maybe I have to let me try something here. I'm gonna refresh group folders. Okay, yeah, see, I see your spreadsheet there. Maybe I will delete some of the old files. I'm suspecting that's the problem. We'll remove this one. Okay. I'm also going to remove this one here. We're getting this message in upspace, let's say. Storage, making for the memories. It's in trash or spam. Okay. Emails in trash, emails in spam. Review and clean up. Maybe that's the problem. Let's see. Delete all. Review, out in trash. Emails in spam. One more student. Okay, I still see. Let's go to the other students. Let's see. That's 4. Okay, so here you go. Download, right? Download files. Okay, so you said you don't see the files there, right, Randy? Okay, let's see. Vanessa Bonilla, are you there? Okay, can you do you see the file there, the spreadsheet for lab 2 there, Vanessa? Oh, you do see. Okay, so Vanessa does see it. So let's see. What about Ashley? Is Ashley there?
Yes, I'm here.
Okay, do you see the file there, Ashley?
No, I don't think so.
Don't think so. Group number 2. Group number 2. Yeah, I see your file there. Okay.
Okay.
So, okay, don't see it. Okay. Randy doesn't see, but Vanessa sees. Vanessa's group number 5. Natalie, are you there, Natalie?
Yes, I'm here.
Do you see the file there in your group folder?
Yes.
Yes, okay, thank you. So share the file with Ashley, if you may, please. Since you're in the
Okay.
same. Jeanette Garcia.
I'm here.
Okay, do you see the file there in your group folder, Jeanette?
I don't see it. I only see the last
Oh.
one.
That's strange. Okay, let's find out. You know, I don't know, refresh the screen or reboot your computer, you know, I do not know.
Yeah, I'm refreshing the screen to see if it comes up.
But it's not. You might also want to close the browser and open it from scratch. Maybe it will show up. As a last resort, you know, just restart the computer, right? Or just get the file from Natalie, who can see the file there. Noor, are you there? Okay, I see Noor here in my. Are you there, Noor?
Yeah, she's here. She just had to
Okay.
step away for just a second.
Okay. Does she see the file there? Do you know?
She wasn't able to see the file either.
Okay, I'll put a no here. And Blanca Hernandez.
Yes, I could see the file.
Oh, you can see the file. Your group number 5. Okay. Group number 3, Kaylee Hernandez.
I'm here.
You see the file there, Kaylee?
No, I don't have access to the files right now.
You don't have access. You don't have access to what do you mean? You don't see the files, or?
No,
You don't have-
I'm on my phone, so I can't check it right now.
Okay, okay. You cannot check right now. Okay, you can't check. Okay. Joshua Jimenez. Are you there, Joshua?
Yes, and I could see the graph. My
You
group and I
see the
shared it already with each other.
Okay, so you can see the file, right?
Yeah.
Group 5, huh? Interesting. Group 5, and group 5, huh? Group 5 have no problem. Let's see. Next is Alondra. Are you there, Alondra?
Yes, I am.
Do you see the file there in the group folder?
Yeah, I see the file in my folder.
Thank you. Group 3, Kennedy, you don't see, right?
No, I refreshed it. I closed the browser, opened it again,
Okay.
and I'm not sure what the issue is because it's
I'll
not
do
just
something.
me, but it's the other people in my group as well. So
Mhm. I'll do something here that might be going to work. Let me finish with the attendance here. Daisy,
Okay.
Mariska, are you there, Daisy?
I'm here.
Okay, do you see the file there?
Yeah, I can see it.
I can hardly hear you.
I said,
Yes or
yeah, I
no?
can see it.
Yeah, yes, okay, good, thank you. 6, group 6, and next is Yesenia. Are you there, Yesenia? Yesenia. Okay, do you see the file there in the group folder, in your group folder? No? Okay. Okay. So Ryan Ong, are you there? I have it. Okay, so you see the file there. Your group number 4. Artur Pacheco, are you there, Artur? I don't see Artur here. Artur. Nope. Lady Lud, are you there?
Yes, I'm here. Yes, I can't see the file.
You see the file? Okay, good. Donia?
Here. And yes, I have it downloaded.
Okay, so you see the file there. Elika, what say? I don't see Elika here. Brianna Valencia. Okay, good. You can see the file, group number 1. Justena Youssef. Okay, do you see the file there in your group folder, Justena? Yes, okay, good. Good. Let's see what are the problems. I'm gonna sort that out here and find out what are the groups are having problems. Okay, group 2, right? Group 3, group 4. Just Yesenia is having a problem in group 6. So we're talking about groups 2, 3. Okay, let's start with group 2 and 3. I am going to delete this file from group 2 and I'm going to re-upload it. Okay. Group 2. Okay, I'm going to do the same with group number 3. Okay, okay. File disappeared now from group 3. Let's put it back there. Let me. Group 3. Okay. File back there. And only one student in group 6 had problems, right?
Okay, I can see the second document now, or
Okay,
the second
good.
Excel.
Okay, good. And just a matter of deleting it and re-uploading it. Sometimes that happens. Okay.
Mhm.
Now, Yesenia, do you still don't see it? Is Yesenia?
Jesus.
Let me do that. Let me delete. Let's see. Group 3, group 2, group 3. Okay, just number 6 now. I'm going to delete this file and re-upload it. 6. Good. So let's start with the lab now. Today is electric field 2, so here you go. What you see for let's see what you see now in today's experiment, right? experiment between quotes. The model you have is that of a point charge. Okay. The first approximation. We can say that the first approximation, right? First approximation is not exactly that of a point charge, but it's close enough. Okay, it's close enough. And I'm going to open one of those spreadsheets here. Okay, that's how it looks like. That's how the spreadsheet looks like. Similar to what you had before, but the geometry of the system is different. The geometry of the system that you have. Let's go from to the first here. We have this resistive paper, which is a black paper. And I get my metallic paint and I drew like a little circle in the center, okay, and a larger circle on the outside. Little circle in the center and a large circle outside. Okay. In the next step, we place this paper on the top of a cork board. The cork board is necessary because it's a dielectric material, it's a non-conductive material. You can purchase that almost anywhere, right? The cork board. The paper is just like 8.5 by 11 paper that we have out there. And the cork board is a little bit larger than that. In the next step, what do? We insert 4 pins at the edges of the paper. We do that just to secure the cork board. I want you to have a picture of what we do, right? And then in the next step, just like we did before, we insert, by the way, a metallic pin in one of the electrodes. It's a metallic pin. It must be a metallic pin to make electrical contact with my battery. Okay. You can insert this pin anywhere in this layer of metallic paint. Because the metallic paint is a conductive material. And then we insert another pin at the center electrode, the middle electrode. In the next step, we're going to power our power supply or our battery and set it to 10 volts, just like we did before. My source of electrical energy. Okay, and connect the outer electrode to the negative of the power supply. Okay, using a black cable. And connect the inner electrode to the positive of the battery using the red cable. Red for positive, black for negative. Red for positively charged, black for negatively charged. Connect one end, okay, and now we are going to we connect the battery. This guy here, this electrode is charged right now. In this very moment, we have an electric field coming out from the center of the paper, going towards the negative ring. Okay, the negative ring of this electrode. Okay, and we are going to get a multimeter. We're going to connect the negative of the multimeter to this outer ring. To this outer ring. And we leave it there. My Here you go. Here's my multimeter here. My multimeter comes with those probes. Every multimeter comes with a probe. Okay, the negative is connected here. Negative probe is connected here, and we touch the we secure, right, this pin here in the negative of the electrode. The positive. No, we leave it suspended like that. We leave it loose, just like we did for the other one. And that's going to be the probe that's going to be making the measurements. Between this point and this point, we have a 10 volts of difference. Okay, connect the other end of the second cable to the outer electrode. Okay, red probe to the red jack. For now, leave the other end of the red probe laying down on the table. Okay, we set an imaginary x-axis through the middle of the paper. It's going to be our x-axis, and we need a coordinate axis, x and y. Keep in mind that this geometry is a little bit more difficult than the other one. This one is going to have circular geometry. The other have a planar symmetry, circular symmetry. The other one that we did had planar symmetry. Here you go. We set the second x-axis, and by the way, that's the x-axis that you see here in this table. That's the x-axis, the values of the x-axis that you see in the table, the y-axis that you see in the table. Okay. Okay, as a check to their equipment, touch the red probe to the pin of the outer electrode. You're supposed to read 10 volts, okay. Now you're supposed to read 0 volts. As a second check, the red probe at several points of the surface of the. So what we do, the negative probe is right in here. We get the positive probe and touch here the spin, and then touch everywhere else, because there is no electrical potential difference along this conductor. You should read 0 volts. This is just a check. This is not an actual data that's in the spreadsheet. Okay. As a third check, you touch the red probe on the pin of the inner electrode. Here you should read 10 volts. 10 volts of electric potential difference if you perform the actual experiment. Okay. And then touch anywhere on the surface of this electrode. Okay. And now we start the actual experiment. Before we start a lengthy experiment, we all can come up with a simple checks. Okay, that's what we did here in those four steps. Okay, this one, first check, second check, third check, and fourth check. It's something that doesn't take too long and allows you to find out whether the experiment is working in a proper way or not. That's why I include those 4 checks when we do that in the actual experiment. Then we start collecting the data. Okay. If we go to our spreadsheet, okay, right here, we start with half volts. That's what we have here, half volts. Then 1 volt. Okay, let's see, half volt, 1 volt, 2 volts, 3 volts, 4 volts, almost 4, right? And 5.5 volts. We're going to collect 1, 2, 3, 4, 5 equipotential surfaces. So, and what I usually tell my students, which is, a very good way of proper experimental procedure. Okay, first we collect the points of voltage only along the x-axis. So we start with half volt along the x-axis. We choose y equal to 0, right? And then you record the position of this point. Get as close as you can to half volt. And then 1 volt. And then 2 volts, 3 volts, 4 volts, and 5.5 volts. If you have any different values, you know, that's not the half, 1, 2, 3, 4, and 5.5, let me know, please. Okay, so those are my first points of my equipotential surfaces. My first point of my equipotential surface is going to be a total of 6 equipotential surfaces. 1, 2, 3, 4, 5, 6. And then what we do next? We get points along the y-axis. Okay, half volt, 1 volt, 2 volts, 3 volts, 4 volts, and 5.5 volts. Okay. 2 points now of our equipotential surface. Let's take a look at our spreadsheet now. Here you go. Here. Oh, here are some of the points, right? Here is 6 centimeters. Apparently this is student, they inverted the x and y axis. Okay, 0. Here, oh yeah, here you go. 6 centimeters here. Yeah, apparently they inverted the x and y axis. And then what else? We go here, we go for the next step, fill in everything else in between. Okay, in the outer surface, we put 4 points between those two, between the points in the axis. And we should get more or less a circle because this configuration has circular symmetry. Okay. Do not get something like that. That's what I tell my students, you know, do not get something like that, a big gap. 1, 2, 3, 4, 5, 6 points is a big gap here. You know, I ask my students when they perform the experiment to strive to get points that are evenly spaced. Okay. And then go for the next equipotential. Okay. Look for 4 additional points in between the other two. Notice that this arc, as you move closer and closer to the center, okay, the arc becomes shorter and shorter, right? It becomes shorter and shorter. So it's going to come to a point that you will have to get points outside this first quadrant. That's why I tell my students, it's very difficult, you know, it's not nice to have points very close by each other. Because you want to see the genetic way that those equipotential surfaces are distributed. So if you did everything right, you're going to get something like that. Okay, equipotential half, equipotential 1 volt. That should be 2 volts. The next is 3, 4 volts, 5.5. Okay. And then you draw, you know, arc of a circle and plot the electric field lines, which, you know, just like before, should be normal to the equipotential surfaces. And normal again means perpendicular to the tangent of the equipotential surface or curve in this case. Okay, so Okay, so that's what we have. Let's start plotting those graphs. We're going to do exactly what we did before. Okay. Open your spreadsheet right now. There's an equipotential of half. Notice that's not exactly half, right? Because it's very difficult to get exactly 0.500. But that's okay, provided you're close enough. Ideally, it should be, less than 5% off of the value if you're measuring half. So less than 5% should be 10% should be 1% should be 0.505, between 0.495 and 505. That would be 1%. 5% would be 0.525. 0.525. If you can get between plus and minus 5%, is fine. Okay, and let's go plot those two equipotentials. Okay, X and R, X and Y. And what about this R? What's this R here? This R, just look at the formula. This R is the square of X plus the square of Y, the square root of that. So it's the radius of the circle that you got. The radius of the circle that you got. You have a circle here, section of the circle, right? You have the X and Y position of this point, X and Y position of this point, X and Y position of this point. If you got the proper points, you should get R value that's very close to each other. And here you go. And what am I getting here? I'm going to display that for you. They're not going to be exactly the same. They should be close enough. Yeah. 0.061, which is 6.1 centimeters, 5.8 centimeters. You can see it's very close to each other on the average. Okay. Those X and Y, let's write it down here. X and Y are measured. X and Y are measured with a ruler. The ruler is that has a resolution of 0.001 meters or 1 millimeter. So make sure you display it with the proper significant digits. Okay. The V values are measured with the digital multimeter DMM. Use the table in PDF format. Use the file in PDF format to determine their significant digits. Okay, and let's plot our graph, our first equipotential. Insert charts. Here you go. Because this is supposed to be a circle, we should adjust the graph so the length here appears to be the same as the length here. So you can visualize what appears to be a circle. It's not exactly a circle, but it's close enough. Then we go for the next equipotential surface or equipotential line. Right here. I want to see this R value here in numeric format. So you can picture it. Number 1, 2, 3. Okay. It should be a circle of lower radius because it's a larger voltage. If here is 6 centimeters, here end up being approximately 5 centimeters. And we are going to plot another. No, it's not trend line, sorry. It's a select data. Let's do it again. Here. Click one of the data points, right click, just like we did before, and select data. Select data. The first one was half volt. The second one should be 1 volt. 1 volt. Okay. X values, you highlight the value, the X values in that column, and Y values. Okay. So we have my second equipotential surface. This group decided to start taking data on the second quadrant in this second equipotential. Click OK. I can also edit this one and write down half volt. Add another one. Right? The next one should be what? 2 volts. 2 volts. X value. No, wait a minute, not here. Volts. X value. Y value. And Y value. Click OK. Oh, wait, what is it showing up here? Huh. Let me erase it. Didn't erase it before. No. Okay. There's a problem here. I don't know what's going on. Ah, I know why. Okay. It's the equal sign, 2.0 volts. Good. You cannot have an equal sign here. This one has to have an equal sign. Now we have our third electric potential. Let's move it. Okay, go. Next, select data. Add one more. What's going to be the next one? 3 volts. 3.0 volts. Select X and Y. Click OK, right? And finish. And finish that up. Add 4 volts. X and Y for 4. We're gonna see how this graph is going on. Okay, here you go. Half, 1, 2, 3, 4. And the last one. It should be 5 volts. Click it here, and then we have it. Here you go. We have all the surfaces here. about the equipotential surfaces. So let's, any questions? Let's take a look at the R values again. I'm going to display that in the normal format, so you can read those more easily. Number. Okay, 3.5 centimeter, 2.4 centimeter, almost 2, 1.2. That's what those radii are all about. It's like 10 o'clock already. We need our break. Want to make? Did you manage to do that? Plot equipotentials. Let's take our break first. Okay, and then we back from the break. We are back from the break. We will. I will ask you if you are able to plot the equipotential. Okay. Notes right in here. Break from, let's say, 10:05 to 10:20 a.m. Any questions again? I want to encourage you to ask questions before you go into the break. You plotted those equipotentials before, right? So you shouldn't have any problems plotting them again. Okay, so I see you, that there is no questions. I see you in 15 minutes again. Okay, so now I'm gonna go one by one, see if you had any problems plotting the graphs, okay? Let's start with Brianna. Brianna, were you able to plot the equipotentials?
Yes, I was.
Okay, good. Do they look like just like mine, like that? Right? They look just like that, right?
Yeah, they look pretty similar.
Okay, good. So don't forget to add, right? Don't forget to add the X and Y labels to the graphs. And oh, one more thing, right? You gotta draw an average circle around here for each of those equipotentials. 1, 2, 3, 4.
So we add lines kind of like the first lab, right?
All of them. Yeah, just yeah, all of them.
Okay.
You can do it by hand, or maybe Excel has this capability. Let me check here. I don't see something to do with Excel, but at least with, by hand, you might be able to do that. And don't forget also the electric field lines. The potential is increasing from the outer ring to the inner circle. The electric field has a opposite direction, just like we had before here, right? Positive to the negative. Do you see the pattern? It happens for every charge distribution. The electric field starts on the positive charge and ends on the negative charge. The The only thing that changes what's the format of this line. Okay. Let's go for the next student here. Brianna managed to do that. Next, oh, yes. Justena, were you able to plot the lines? The graph? Justena, I don't hear. Oh, still working on that. Okay, still working. That's good. I'll put a W here. Ashley, were you able to plot the equipotentials?
Yes, I was.
Okay, good. Thank you. Do you have any questions?
No, thank you.
Okay. Next one here is Natalie.
Yes, I was able to.
Okay, good. Don't forget. Any questions, Natalie?
No questions. Thank you.
Okay, thank you. Jeanette,
Yes.
okay, were you able to plot
Yeah,
it?
I was able to get the graph.
Okay, and don't forget there's more to it, right? You gotta,
Yeah.
put everything with the right number of significant digits. And one more thing that needs to be done. Okay, before, let's see, there's one more thing that needs to be done, okay? Oh yeah, I didn't tell you that. That's the first graph. That's the first graph. Okay, there must be a second graph as well. The second graph, you're going to plot the voltage and the average position. Average voltage and the average position. But it's going to be an average R, okay? What you see here is not going to be X or Y. It's going to be the radius R. Remember that I told you that this electrode distribution is very similar to that of a point charge, right? So when you plot voltage against R, you might be able to see that dependence of a point charge. I'll do that right now. Okay, here you go. That's what I'm getting for my set of data. Here in the vertical is the voltage, here in the horizontal is the radius. And then there is one more thing that you have to do. You have to fit a power fit to this data. Excel allows it. This is not a straight line. You can see that this is not a straight line, definitely. But Excel allows you to fit curves other than the straight line. And let's do that together. That's new for you, okay? That's something new for you. You're seeing that for the first time. Just like before, click one of the data points, right-click it, add a trend line. Okay? Because it's clicked linear, your linear drawing showed up here, but you don't want linear. You want a power fit, this one right in here. Okay? You want a power fit. You're going to display the equation chart right in here, okay? And you're going to display as well, what happened to my? You're going to display as well the R square. And where did it go? Okay, I'll have to do that again. Add trend line, okay? Power, right? Display the equation and display the R square. What you're getting here is not the power of -1. It's power of -1.4. It's not a perfect fit. Your R square is pretty high. Okay. So first approximation, we can say that this distribution here is that of a point charge, but in reality it's not. In reality, this is not a point charge distribution with a ring around the point charge. In reality, what this distribution is all about is a cylindrical distribution of charge. Okay, you have a cylinder coming out on this page and another hollow cylinder surrounding the other one. Okay. That's why we are not getting a good curve fit for the point charge. Okay. So that's why I asked you here in this table, not only to come up with a power fit, but also to come up with a logarithmic fit, which, by the way, is exactly the relation for the electric potential of a cylindrical charge distribution. Okay, so in addition of plotting of getting the trend line for the power, I want you also to get a logarithmic trend line. Now compare those two here. Which one has a better R square? And even the line, right? The line is much closer to the data points, whereas this one deviate a little bit from the data points. Yeah, I'm gonna put it right in here. Look at the R square of the logarithmic and the R square of the point charge.
Professor.
Yeah.
Okay, so we want to get the line that's connected to the dots and not the power line that goes above where the dots are?
You want both of them.
Or you want both? Oh, okay.
Yeah,
Sorry.
you want both of them. See, power fit. You have this equation here.
Yeah.
You
Right.
copy it, right? And you paste it here, and then you work it out. Oh, no, didn't work. Let me try again. Yeah, now I might want to put R here, and instead of X, and raise this one to the power upper script font superscript. Does it look like? Yeah. Want to make it look nicer? Italicize it.
Okay, so then we'll have the trend line like slope values for both.
For both, yeah.
Gotcha. Thank you.
Yeah, don't forget the R square too. Don't forget the R square. Okay. This is the type of thing that we do whenever we're doing research. Okay, we try to fit a mathematical model to our data to make sense of it. Today, with softwares like Excel allows you to fit all sorts of curves. Well, not all sorts of curves, a few type of curves, right? Let's take a look here. Not only have the linear, but you also have exponential, logarithmic, polynomial power, and we have this moving average. This moving average is used mostly for whoever trades stocks, if you're plotting the price of a stock, moving average of the price of a stock, you want to use this trend line that you see here. Let me. So Excel, make it available to you 1, 2, 3, 4, 5, 6 different trend lines. 6 different trend lines. Of course, there are infinite number of almost infinite number of functions out there, right? But they make it available only 6. Nature is interesting because most of the processes of nature are linear. Yeah, it's a kind of interesting. That's why we. But then there will be many other out there that are not linear. That would be exponential, would be logarithmic, would be power.
Professor, how do you do the superscript again real quick for the R2?
Okay, so let's do it. I'm gonna copy. First you have to copy, right? Do you do that?
Yes.
Okay, you copy, right? And I'm gonna do from scratch, right? Copy and paste. You go. I don't want the X in there because it's not the X that you're using. You're using the R, right? It's the radial distance from the point charge. The italicize is easy, right? All you gotta do is to click the italics here. to see the italic font. Now, what about the superscript? The superscript, you highlight everything here, okay? And you go to font. See the font here? You can also, maybe you can also, yeah, you can, no, this one is not gonna have it. Oh yeah, it does have it. Yeah, you gotta go to font here. The other option doesn't have it. Go to font, click this little arrow, and we have those choices here. Strike out, strike through, superscript, subscript. Superscript.
Oh, I see it now. Yeah, I did it. Thank you.
Sometimes sometimes you can also find that just by right clicking it, but I didn't see it. Smart lookup, format cell. Maybe it's here in format cell. Let me see. Yeah, see the superscript listed. So that's another way of doing it. We have this option. Doing right click sometimes is far more convenient than looking here at the top, right? Let's see this power. And then the other one, logarithmic. In order to derive this relationship for the voltage logarithmic wise, you need calculus. That's why we didn't do that in the classroom. Go. Right, log is not log of r, is not log of x, is log of r. And I'm going to italicize this number. It's not, doesn't let me do that, and I know why. Maybe it will let me do now. Yeah, now it let me do. See, it doesn't like the number one in front of the number. When you put the number one there, he's expecting me to enter an equation, and so he grays out the choices. So there's a little trick that you have to do. You put a -1 between parentheses, like that, and put that. And now I can italicize my R. Extend a little bit. Okay, this value here, has a negative 8.3 because this function is started somewhere around here at 8. With r squared. Okay. So choosing you have to do. Where did I stop? I stopped at Randy, right? Randy, did you plot? There's the equipotential, and then there is the other plots.
Yeah, I'm still working on it, but I'm getting it.
Okay, good. You didn't finish yet, right? The equipotential still didn't finish, right?
Correct.
Okay. V versus R. Okay, so I'm gonna put it working. Next is Noor. Did you finish the equipotential plot, Noor?
Yeah, Professor, all good.
Yes, okay.
Yes.
What about the other one?
I'm doing it right now.
Okay, good. Working. Kaylee? Is Kaylee here? I don't see Kaylee. Okay.
Yeah, Kaylee was having internet issues, but I know that she was working on it.
Really? She's on group 3, right? Okay.
Yes, sir.
Ask her to, if she can send me a text message.
All right.
Okay. No connection. No connection. Okay. Kennedy, did you plot the first the equipotential? The first one?
Yeah, I'm working on the second graph. I'm almost done with it. I'm just inputting the values into the 2.3 table.
Okay. Ryan? I graphed both, just need to add labels. Okay, good. Thank you, Donia.
I'm still working on mine.
The first or the second?
First one.
Ah, okay. Good. Vanessa? Yeah, I thought let's to work on this the other. Okay, thank you. Yes, W here. Blanca Hernandez. Blanca. Are you there, Blanca?
Yeah, it will be the same answer from Vanessa's.
Same as Vanessa. Let's see. Where is Vanessa? Ah, Vanessa. Okay, yes, and working. Okay, good. And Joshua?
Yeah, we got both of them.
Both of them? Okay.
Yeah.
Let's start working on the significant digits and the units, please. Next is Alondra. Okay, good. Daisy.
Yeah, I'm done with both.
Both of them? Okay. And let's start working on the units, right? And the significant digits. Yesenia. Oh, you're done. Okay. So thank you, Yesenia. Labelud.
Yes, I finished the second graph.
You finished the second one?
Yes.
So you did both. So please start working on the units, right? And the digits. Next, let's go back here. Brianna, I didn't ask you whether you plotted the second graph.
Yeah, I have both of them done.
Oh, good. So, okay, so Justina, did you manage to finish the first graph? Yes. What about the second? Yes. Okay, good. So please start working on the other, right? The units and the significant digits. Ashley Diaz.
Yes.
You did both of them?
Yeah, I have both of the charts done.
Okay, good. Any questions?
No, I'm doing good. Thank you.
Okay, thank you. Natalie,
Yes, I have them done.
you have done. Okay. Good. Any questions, Natalie?
No, no questions.
Okay, thank you. Jeanette,
Yeah, I have them both.
good. Thank you. Any questions? Okay, let's move to Randy. Randy, did you manage to finish the first plot?
Yeah.
First plot you managed. What about the second one?
Yeah.
Oh, yeah, okay. So please start working on the units. And okay, Donia, right? Let's see, where is Donia here? Okay, but I got the first plot. Okay, good. So you start working on the second. Let's see. Noor, did you manage to finish the second plot?
Yes, Professor.
Okay, thank you. And okay. And Kennedy, a little bit early, right?
Yeah, I was trying to follow along with you.
Okay. Oh, you want me to plot it again?
I think I got it.
Mm-hmm.
Yeah.
Yeah. Don't forget, we still have to put the labels there, chart design, add chart element, axis title, primary horizontal. Primary horizontal is R. And then you put between parentheses meter.
Professor, I have a question.
Yeah.
To be able to turn the numbers into decimals, do we have to highlight the boxes and click and right click?
Yes. Are you talking about those numbers here?
Yeah.
Yeah. Right click. Right. Format cell. And then you go to number here. And then you can change from scientific to number. Okay, so there's two those tabs here, right?
Okay, and then you just go to scientific?
No, you change, right? You change from scientific to a regular number.
Okay.
You change from scientific to a regular number. Okay.
And then it should show up as the new number?
No number? What do you mean?
As like instead of there being a number, it goes into a decimal point?
Okay, so here you go. Let's do it again, right? Right click, format. Okay, if I put number here and I have 0 decimal places, right? What's gonna happen? It's gonna show only something like that, right? Because I don't have any decimal places there. Make sense?
Yeah.
But then, yeah, what do you have to do? You have to add decimal places there, right? Number and 1, 2, 3 decimal places. Right now it shows everything.
Okay, I get it. Yeah, I get it. Thank you.
Okay. It's 3 decimal places because it's a y is a coordinate, and you have to display after the 3rd decimal place of your measurement.
Right, so we just follow the chart that you gave to us for the first lab, right?
The chart.
Pretty much. When it comes to significant figures, I mean.
Oh, yeah, the significant figures. Well,
Okay.
remember, right? Here is going to be 3 decimal places, right? Everything here is going to be 3 decimal places, X and Y. But here is going to be different, right? Depending on your number.
Right.
You
Okay.
check your table, right?
Okay. X and Y are 3. Gotcha.
Yeah, X and Y is 3 decimal places, not 3 significant figures, right? And then you have the R here. You have the, oh, wait a minute. The R is in red. You don't need to display significant digits, but you need to display significant digits for the voltage.
Okay. But just for the R, we just use regular numbers instead of scientific notation.
Yeah, and you don't have to worry about significant digits here. You do have to worry about significant digits here because this is an average voltage, right? Let's put AVG. So I am
okay.
Just like we had before, you had an average voltage there.
Gotcha.
Gonna be the average of those. So we go R, and we'll have to add chart element, axis title, primary vertical. B AVG between parentheses volt. What is the 18, 16, 16? It's trying to come in. Average. Font. Subscript. Go there. And we can also change that font, change that to 12. 9 is too small. And I also like to do bold-faced. That's what I do in my papers. And instead of putting the exponential, right? You gotta change also the format. Format, font, format axis. Yeah, format axis number. And then instead of scientific, you put number. And 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. And here 2, 12. Fonts right in here. 12. I like bold faces in my axis. And I also have to change the number instead of scientific. We put regular number with 2 decimal places, otherwise you're going to have only zeros there. 1 centimeter, 2 centimeters, 3 centimeters, 4, 5, 6, 7.
Next.
The 2 graphs, and that'll do the same for this guy here. 10, 40, 10, 50. Get some water here. Let's go for our break. Play. And okay. Screen. Okay. We're back here, 11:05. Let's see. B versus R. Okay, so most of you finished the second plot, right? Just a few of you didn't get the second plot. Let's see. Did you finish, Kennedy? Did you finish the second plot?
Yeah, I was done with the second plot a little bit ago.
Okay, good. Any questions?
Not currently.
Okay. Okay, Donya,
Yes.
you finished? Okay. And Vanessa Bonilla? Is Vanessa there? Vanessa Bonilla. Okay, I can't hear anything from Vanessa. Let's go for Blanca. Blanca Hernandez.
Yes.
You finished second plot? That's good. Any questions, Blanca?
No.
Okay. Alondra, did you finish the second plot?
Yes, I did.
Oh, you did? Okay, that's good. And Kaylee's having problems, right, with her connection.
I'm back again.
Okay, were you able to plot the 2 graphs, Kaylee?
I'm not done, but I'm almost like caught up. I'm still catching up.
Okay. Okay, so let's see what else we have. So what's new about that? This the so-called experiment, right? What's new about this experiment is this one here. This one that have 2 different curves. Okay, there is a mathematical method to derive those curves. This mathematical method is taught in statistics. The derivation, the mathematical derivation is easiest for straight lines or linear fitting. And it becomes more difficult as you go to more complex functions. Okay. And even I myself, I do not know how to derive. I know how to derive the equations for the regression equation for a linear fit. I know how to do that. But for the other functions, I still don't quite know. Still don't. But I know the principle behind that. Okay, I know the principle behind that. What's the first step to derive the equations? But the derivation has to be rather difficult. It's not easy. Everything linear, you know, it's rather easy to deal with. When it comes to square, cube, log, powers, things start to become more difficult, okay? And I want you also, don't forget the CL, right? Don't forget the CL here. We do not have percentage differences in this case. In this case, we don't have a percentage differences because we do not have what compare that with. So there's no need for that. And going back to the plot. Okay, so plot the V versus R, right? What else you have to do? You know, fill up the units. No, before fill up the units, right? Make sure you have, you label the axis of the graphs. Okay. And find of the plots and find the trend line for the second one. Okay. And find the, no, not the trend line, find the regression and find two regression equations for the second graph. That one, and there's going to be a power fitting and log fitting. Okay. Plot. No, fill up the units on the tables. Display the correct number of significant figures. Okay. Display R squared. Find the CL. Find the CL for both curve fittings. Is that all we need? Number of data points, 1, 2, 3, 4, 5, 6. Is this, don't forget, it's the same data that we are plotting here. It's just we are fitting it with a different regression equation. We're fitting it with a different regression equation. Because the R square is larger here for the log fitting, it means that the logarithmic curve fits better than the power curve. And when you go to find out which electric charge configuration has this logarithmic behavior, you find out that it is the cylindrical distribution of charges.
Professor?
Okay? Yeah.
Sorry, for the logarithmic fit, you put for the V average, right, in table 2.3, you had to put -1 in parentheses, and that says multiplied by
13.
the Y.
Oh, I put wait a minute, I put it's not 13, it's 3, right?
Yeah, it should be the
multiply
Y
by-
value for, right?
Well, it's not y value here.
Oh, no, I just mean that shows in the chart. So the -3.117, I think. I can't really read it.
Yeah, that's right. It's -3. I put the -1 between parentheses for a reason.
Yeah, because it'll show up as something
Yeah.
else. Okay.
So,
So
yeah,
-1 times that. Okay.
yeah, like that here. Let me see if he, yeah, see, he doesn't like it. So I gotta go back to the negative.
Right.
And the star is for multiplication. You know, that's a quirk of Excel. You know,
Thank you.
if I put a negative there, he thinks I'm gonna type a formula. So I have to put that parenthesis to trick Excel that this is not a formula, but just some text that I'm putting there.
Thank you.
Okay. Welcome. R squared 0.9961, right? Blah, blah, blah. The other one is 0.9332. Oops. 0.9332. Okay. Any more questions? 11:15 right now. We have 45 more minutes to go. What I want to do, if there's no question about this lab, just prepare it. Let's take a look at this at the schedule. Okay. Schedule. Okay, next Wednesday is going to be an exam. So this report is going to be due the other Wednesday, okay? Lab to do, let's put it this way, lab to do. Report for lab to do. This should be lab 1 do. Lab 1 do. I put only 2 chapters here, remember that? Let us cover the important equations for this exam. There are, in physics, there is some things you can derive. Most things you can derive mathematically, but then there are some other things that you have to memorize no matter what. Okay. And I want you to be aware of that. What do you have? This one, here you go. Got it? Those are the chapters, the sections. I want to have my book side. Oh, here you go. Here's the book. Side by side. (18) origin of electricity. Let's cover the equations that you have to know, right? Equations for the exam. The first equation is going to be the electric force. The same force that the ancient Greeks would call magnetic force. They didn't know it was a different type of phenomenon. It was easier for them to observe magnetic phenomena at that time than to observe electric phenomena. Okay, and what's the electric force? Electric force is electric force between 2 charges, K, Q1, Q2, Q2 over R squared. This is you have to memorize. Because it's a law, Coulomb's law. Coulomb's. Nobody can derive this equation here. This equation here can only be determined by performing experiments. That is the first equation that you have to memorize. And it's called Coulomb's law. And then you have the electric field. Electric field. That's a definition. Listen, this is not a definition. No. Definition. The electric field is defined. The electric field, I'm going to write like that. You go, the electric field of charge 2. I'll go even further than that. Charge 2 is defined as being force between 1 and 2. Let me label it between 1 and 2 divided by charge of 1. That's a definition. This is not a law. It's a definition that ends up being very convenient to know. For a point charge, the electric field of a point charge 2 is going to be given, point charge Q2 is going to be given by something like that. Similarly, the electric field of charge Q1, right, is something like that. That's the second definition that you have to memorize. That's the first definition that you have to memorize. This is a law. This is not a definition. And electric field lines, there is no formula there, but there is some interpretation that Gauss's law. Okay, Gauss's law is nothing but the Coulomb's law in a different format. Gauss's law, Coulomb's law in a different mathematical format. And okay, so how do we formulate Gauss's law? The flux, the electrical flux through a closed surface is equal to the charge enclosed by that surface times 4 pi k. This is another law. This is the same law that you saw, but in a different format. Okay, and you have to memorize it. Epsilon. No. The other way to formulate that epsilon is to formulate without the 4 pi k. How is the electric flux? We're going to see, by the way, we're going to see something like that in the future, not for the electric field, but also for the magnetic field, okay? So how do we define the flux of a field? It's going to be the field itself, the area through the Gaussian surface multiplied by the cosine of the angle between those two vectors. I call this angle theta. Depending on the surface that you choose, the angle is going to be a given angle, just like you saw before. Depending on the closed surface that you choose, you may have different angles for the same problem. Okay. Gauss's law. Then we have the potential energy. Electric potential energy. Electric potential energy definition. That's another definition. This definition comes from the definition of potential energy we saw in physics 6. Okay, and the definition is electric potential energy is minus the work done by the electric force minus the work done by the electric force. And then we have the electrical potential. Electric potential. This is defined. This is defined in terms of the electric potential energy. Okay. So the electric potential, we call it B, is electric potential energy divided by a test charge Q. Here let's look at the units, right? I didn't put the units here. Doesn't matter if it's an electric force. Doesn't matter, it's a gravitational force. Every force has the same unit. It's the unit of newtons. For the electric field, right? It doesn't matter which electric field of any charge distribution we are talking about. The unit for the electric field is going to be newtons per coulomb. In the case of the flux, electric flux, well, in order to find out what the units are, all you have to do is to do some dimensional analysis here. Okay. It's going to be the unit of the electric field times the unit of the area. Cosine of theta has no unit whatsoever. Oh. So we combine those units that you saw before. Newton per coulomb, meter square. Electric potential energy, just like any type of energy, is going to have the unit of joules. And here for the voltage, is going to be joules per coulomb, which, by the way, we call volts. You see that so frequently that we call that volts. We do not have any specific unit for that. Okay. And we are in voltage now. Electric potential of a uniform field. Oh, before we go there, right? Before we go here, let me fill up some other formulas here. Okay. E field for a very large plate, charged plate, very large charged planar plate. Do you remember that? That's going to be, it's no longer of a point charge, Let's see here, electric field definition. The way we gotta do here, I wanna reorganize that, okay? That's the basic definition. That's the basic definition of the electric field for a point charge. Okay? It's like that. Charge. Here is going to be what? Sigma. We derive that, okay? By the way, 4 pi k of a single, let's say, of a very large, of a single large charged planar plate is going to be something like that. 2 pi k, which by the way is sigma over epsilon naught. Oh, there's a 2 here. Let's not forget there is a 2 here. And this sigma, what is the sigma? Is the net charge divided by the area. Okay, if field for 2 charged planar plates, one positive, the other negative, one positive, the other negative, is going to be 4 with the same charge density, one positive and the other negative, same charge density. And now it's going to be like that. And I'm going to be even more specific. See if I can find it. Where is that? Okay, I got it. Single brackets. This one I want. Okay. Between the volumes of the plates equal to 0 outside the volumes of the plate. Here it doesn't matter because the field is going to be the same in both directions. We don't have a volume, right? We just have a planar surface, a single planar surface. Okay. Electric potential of a uniform field. Okay, we did that. It's going to be, proportional. Proportional to x, the distance from the plate. Where the proportionality constant, the slope is going to be the E, right? Like that. Okay, like that. And electric potential, not of a uniform field, but of a point charge. This one we can derive. This one we can derive using algebra. Okay. This one we cannot derive using algebra. We need the calculus. That's why you have to memorize. It's going to be KQ over R. Electric field is R squared. Electric potential is over R. And then you have equipotential surfaces. You also have electric field lines, like I mentioned before, right? And the next one that you have to memorize, definition of capacitors. It's amazing that people found that out over the years, right? That if you can get two conductors, one negatively charged or the other positively charged, they have this specific value that's called the capacitance that's dependent only on the geometry of the charge distribution. Even though you have Q over V here, the Q and the V ends up canceling. Why is that? Because this V here will always be proportional to the charge, okay? And the proportional to the charge means we have a constant here that's dependent on geometry of the problem. This Q cancels out, and what's left is a value. You know, I'm gonna put here geometrical, depends on the geometry of the distribution of the charges. Those Q. So people found that out about this definition. So the planar capacitor has one equation for the capacitance. The spherical capacitor has another equation for the capacitance in terms of its geometrical configuration. Okay, capacitance for the planar capacitor. One positive and another negative plate, each of area A, separated by a distance D. So we derived that. Because we knew what the V was all about, we substituted in the equations, and we got that was a function of the area divided by D, and then we have a constant here too, right? You can check there. So I'm gonna put just, I don't remember the constant what it is, but I'm just gonna put a proportionality here. You can hand that down what that constant is all about. Okay. Something like that. Even better. Let's find out. It's written here, right? Let's find out. Okay, that's for the spherical capacitor. All right. And that's, oh yeah, is the epsilon naught. See how epsilon naught shows up so frequently. Okay, so we have those two here. One is the spherical capacitor, the other is the planar capacitor. A over D. Which can also be here written in terms of that K constant that you were first introduced to. Capacitance for the spherical capacitor. Spherical capacitor. Of the concentric capacitor. One of radius A and the other of radius B. Okay, it's like that. You derive that Here becomes 4 pi. So not. Well, you can write it. Let's see. 4 pi epsilon naught over 4 pi k, right? Yeah. 4 pi. Yes, it's like that. Four pi, and then there is no k here. Concentric capacitors and dielectrics, and these equations are good only. These equations for the capacitance, these last two equations, right? These last two equations for the capacitance are good only whenever you have air or vacuum between the conductors. Okay. However, if you have a dielectric, they must be changed. They must be changed. You have a dielectric. If you have another type of dielectric, other types of dielectric, are in vacuum, by the way, they are dielectrics. They must be changed. Okay. The capacitance, the new capacitance becomes, multiplied by a dielectric constant that we call kappa. Yeah, it's not the same as this K here. Not the same as this K here. What else? Definition of capacitance. And there are tabulated values for kappa for different type of dielectrics. Okay. Recall that this kappa comes from that relation of the electric field, right? The electric field, whenever the dielectric is air or vacuum, is given by E naught. Okay, it's going to be something like that. In other words, the electric field decreases by kappa. And we have, let's see, 1142, we have energy, the energy of a capacitor, right? The energy of a capacitor. There are different ways of writing this energy of the capacitor, but the one that I recommend you to remember is the energy density, right, of any capacitor. Any capacitor. U, which is delta U over delta V, is equal to half capacitance times delta. Let's put V instead of delta, V squared. If you have a dielectric there in between, then you have to divide the thing by the kappa. Oh, yeah. Oh, man. Yeah, by the kappa constant. Remember, this kappa is one for air and vacuum. by using this definition here of capacitance, right? This original definition of capacitance, you can get different relations for the, oh, wait a minute. No, it's not like that. Sorry, folks. The energy density is not this one. This one is the energy, potential energy. I don't want to lose my work here. So let's okay, that's the potential energy of a planar potential energy of a planar capacitor. And then the energy density of any capacitor is the epsilon naught E square. The capacitors. Let me double check that's the right one. Maybe storage, energy, let's look at the energy density. Yeah, okay, so we have a kappa here. Kappa is upstairs. According to the book. Okay. Yeah, the energy, the kappa should be upstairs too. Let's see. Derive that. Okay, according to the book is like that. And by the way, this is interesting because we have something similar. We have an equation similar, not for the electrical energy density, but we have a similar equation for the magnetic energy density, not of any capacitor, but any inductor. We're going to study that later on. And that is going to be something, you know, here's the electric field, here's going to be a magnetic field, okay? And then I'm going to put a proportionality constant, okay? It's going to be not epsilon naught, but it's going to be mu naught. And it's going to be divided, it's proportional to that. You can see that it's really interesting that even though we have two different phenomena, their equations for the energy density is proportional to the square of the field. Okay. I'm going to post these notes here. And so you can have fresher memory on the equation that you have to know. Okay. Any questions? $11:47 now.
I have a question.
Yeah, go ahead.
So in regard to the capacitance, you had mentioned and also noted the geometry makes the difference. Does the book dive deeper into that? Because I noticed that there was some stuff that you had said that wasn't typed out. And I just want to make sure that I have a full grasp of everything.
I typed it here that the capacitance depends on geometry, right? That's what you're asking?
No, yeah. No, you typed that there, but I believe you also had mentioned a few other things that weren't noted. But I suppose they're not necessary for the formula.
Well, you gotta tell me which specifically you're referring to. Okay, so So if it's important, I will type there in the notes for you.
Okay. Okay.
Okay. Anything else? Okay, so I'll be here for the office hours, and if you want to talk more about that, we can discuss it here, or otherwise I'll see you next Monday.
Okay. My group would like to talk to you about something because we believe that we know what happened with why we couldn't see the new lab. And so when you said to check to make sure that everything was in, we were when we wanted to double check the files, I saw a new one, but in clicking the lab that we had finished, the second graph was unrecognizable, and we didn't know what happened. So we deleted the other things, and I believe I deleted it, but could I just wanted to make sure that you have the right version of our final first lab, if that's okay.
Let me stop the recording here when